So I will just continue where I started yesterday. So we wanted to look into, like how do these neutrino spectra actually look like? And just to remind you, I mean, the zeroth order paradigm is always, we assume like an e to the power of -2 spectrum, because Fermi acceleration or diffusive shock acceleration is kind of predicting that. So that's what's expected for the primaries, like the cosmic rays, the protons, which would interact with matter or radiation and then produce the neutrinos. So here we have like a prominent counter example. So that's like P gamma interactions, where, for instance, you would produce the delta resonance or some other processes, and then you would produce like charged and neutral pions. And the neutrino spectra in that case, just to remind you, would have like a peak, which is determined by the maximal proton energy or the primary energy, because the neutrinos would follow that. So they take about 5% of the maximal proton energy at the peak. So the cutoff of the protons would directly translate into a cutoff of the neutrinos. And what's happening below the cutoff depends a little bit on the spectra of the initial protons and the target photons. So it's actually inversely proportional to the spectral index of the target photons, because high energy protons interact with low energy photons. So that's essentially a part of the delta resonance condition. You have to match the right center of mass energy. So if you fix this y variable here, like to the maximum, then the higher the proton energy is, the lower the photon energy will be it corresponds to. And this is why you have like this plus sign actually appearing here. At the end, you can see you could also have like an e to the power of -2 spectrum here, as it is kind of like typically postulated if beta is 1. And this is a situation you find, for instance, in gamma ray bursts, in fact, where you have then at the end a kind of like an e to the power of -2 neutrino spectrum. Okay, I will skip. Now it was taking the focus again because the meeting is recorded. So that's the usual Zoom. So I will now continue here. So this is only a part of the story. I mean, you could have P gamma interactions to produce the neutrinos, but there's also other processes. And the prominent process are proton-proton interactions. In this case, you will produce like charged and neutral pions like pi plus, pi minus, and pi zero in about equal amounts. That's not completely true. I mean, you can look, for instance, at that reference if you're interested in the details, but roughly. And in this case, this PP is a little bit misleading in the sense that you actually have something like a non-thermal spectrum of protons, like protons which are like relativistic, interacting with protons which are cold. So this proton is not the same proton as that proton. It's like a thermal proton or a proton which has low energies, okay? And that leads to qualitatively different things. You don't carry the relativistic like dynamics of the target, and you would actually follow the primary spectrum. So I just sketched that here, which was one of the examples which we saw earlier. So in fact, in this case, the secondaries and also the neutrinos, like the pions would decay into the neutrinos, and the neutrinos would also catch this spectrum, would also have an e to the power of -alpha spectrum as this initial non-thermal proton. So in this case, this e to the power of -2 assumption is actually a good one, okay? Then we had, like at the previous slide already, the P gamma interactions. This is just the summary of that. It's also the cartoon of what I was showing before. If you have here e to the power of -alpha, e to the power of -beta for the target photon, you get like this kind of spectrum for the neutrinos. And you get e to the power of -alpha only if beta is 1. And that you typically find in situations like GRBs, where beta is in fact 1 in the part of the spectrum. For AGN blazars, on the other hand, beta is typically larger than 1. So you have this kind of peaky spectra. By the way, this you find in typical examples for this are like starburst galaxies, where you would have like a lot of gas interactions. Starburst galaxies are galaxies which have an enhanced starburst activity and which have like typically like higher gas densities than our density. This is why you would expect to have like a lot of these kind of interactions. And in environments where you have a lot of like gas or dust. And another interesting case, which is the third case in this list, are P gamma interactions with a thermal target. So here we had like a non-thermal power law spectrum of the target photons. But you could have also situations where you have a thermal target photon spectrum, like a black body or a gray body spectrum of photons. For instance, in the cosmic microwave background, you find such a spectrum. But not only there, also if you have like a spectrum produced like by an accretion disk or something like this, which shines. And in this case, in fact, if you look at this cross section, this is the delta resonance as a function of center of mass energy, if you want here. Actually, the effect kicks at higher energies kicks in. So if you go to high enough energies, you have a flat cross section. And this means that at the end, you actually would also follow the primary spectrum if the temperature is high enough. So this is illustrated here, actually, in one of like Damiano's figures, who is sitting here in the back. Okay. There you see like E squared times the neutrino spectrum as a function of energy in comparison like between the delta resonance and for instance, if you take a look at this like a dark blue curve, so that will be the contribution from the delta resonance, or also if you have like a cutoff in the proximal proton energy, which you typically have in ZMB interactions, versus like you would actually take the multi-pion processes into account. And you see that if the target photon temperature is high enough, you also have like a e to the power of -2 spectrum, sort of. And that situation is typically found like in AGN cores or tidal disruption events. So this is why the spectra also look like roughly like e to the power of -2, at least at the peak in this kind of situations. As if you interact with the cosmic microwave background, you would have rather something peaky because the maximal proton energy determines the cutoff. So it's always like a matter of like what determines this cutoff also. And you cannot just rely on this delta resonance approximation in certain situations. That was my point here. So in general, if you wanted to like discuss neutrino spectra and the spectral shapes, you have these 3 cases, I think, which are the main cases. It's still not the complete part of the story, but I will come back to that in one slide. I just wanted to show you like one application actually of this PP interactions here as like an intermediate point. So if you have proton-proton interactions, you will produce, of course, neutrinos, but also gamma rays coming with them. And the gamma rays would carry the same spectral index as the primary protons as the neutrinos do. So they would follow sort of like an e to the power of -2 spectrum. And compared to what I told you yesterday, that you could have like gamma-gamma interactions, which are like stopping the gamma rays in the source, especially in sources with high radiation densities. There are sources where you don't have these high radiation densities, for instance, these starburst galaxies, which have an enhanced star-forming activity. And in this case, you would expect that the output in the neutrinos, which you have, for instance, here as like this dashed thick blue curve here is an e to the power of -2 spectrum fitting the ice cube data, would correspond to the gamma ray spectrum. Here it's a factor of few higher. That's related to the dynamics of these interactions. You can actually check this literature also, like what this factor would be. And in fact, you would have also an e to the power of -2 spectrum for the photons, with some cutoff effects which are well understood. So that's like attenuation in the cosmic microwave background and so on, and in the background lights. So that's like effects which are like coming from the transport, which are well understood. So at the end, you would have like the same spectrum here. And this has implications. For instance, in this case, if you make the spectrum here softer, like the proton spectrum, then you would get this neutrino spectrum here, the dashed, like thin dashed blue curve for the ones who are online. And you would like ramp up the gamma ray spectrum until a point where you actually saturate the Fermi data. So this you cannot exceed because this has been measured. And in fact, this is supposed to be dominated by AGN blazar. So you cannot like have a too large contribution here. And this means that in this kind of like simple relationships or models, you have a direct connection between gamma rays and neutrinos, and you can actually limit also the spectral indices of the neutrinos for these kind of like sources. So that's interesting and has been extensively discussed in the literature. Like one of the people working on that was, for instance, Enrico Peretti, who is going to give a talk later today on a different subject, I believe. Also, Marcus, of course, yeah. Okay, now one exception to this whole game is, so we had like 3 cases before: PP interactions, P gamma interactions with a non-thermal target and with a thermal target. Now there's one exception. You can also do something to the secondaries, like the pions and the muons, which you would actually produce. So far, I have assumed that these pions and muons, they're just decaying in the usual decay chain and nothing happens to them. However, if you have strong enough magnetic fields, synchrotron losses kick in, and pions and muons will be also cooling. So that means beyond a certain energy, they lose energy faster than they can actually decay. And you can compute this critical energy, which is this quantity, which depends on a number of constants. But most importantly, it depends on properties of these secondary muons or pions, like their masses and their rest frame lifetimes, and the magnetic field, which is the only astrophysical quantity showing up there. So if you have strong enough magnetic fields, then you will have an effect which depends on the secondary species, like the pion, muon, or kaon. And that's illustrated here, where you see again E squared times the neutrino spectrum as a function of energy. And if you see as the dashed curves, the spectra without these losses of the secondaries. Right? The maximal neutrino energy would be just following the maximal proton energy, as I was illustrating before. Okay. But once you switch on this effect and you turn up the magnetic field, you suddenly get a split of the neutrino spectra coming from muon decays, from pion decays, and from kaon decays, as it's illustrated here. At these critical energies where you would basically stop the spectrum, so you get a spectral break. That's a technical thing which happens. You could also call it like a cutoff if you wanted. But in fact, what happens is that the spectrum is so-called loss dependent by 2 powers. And that depends on the energy dependence of the radiation processes, which you can extract from the equations I showed you yesterday, if you solve them in very simple cases. So if you had more time in these lectures, like if I do like a longer lecture, we normally also do that actually and try these things, but now I don't have time for that. So that's interesting also in a different context, because what happens here at the peak or in this energy range, actually, there are no neutrinos from muon decays anymore. So it's dominated by pion decays. And pion decay neutrinos, if you look at this decay chain, they only decay into muon neutrinos. And that's what's called in the technical terms like a muon damped source. The flavor composition at the source is like electron to muon to tau neutrinos, 0 to 1 to 0 in this case, in this range. So that's what we call a muon damped source. So in fact, you can affect the flavor composition in the source by these kind of effects. Here, it's also a function of energy, because here, for instance, the muon decays would actually dominate in this small range, where you would have a flavor composition 1 to 1 to 0, because this decay part here dominates. Whereas the standard, just to remind you, the standard assumption is like 1 to 2 to 0, like 1 electron neutrino to 2 muon neutrinos. So this kind of effect is the main effect which typically changes flavor composition, apart from other effects, like for instance, you could have neutrinos produced like from neutron decays, which would only produce like electron flavor, of course. And the typical situation where you find that is like sources with strong magnetic fields, for instance, gamma ray bursts, or like jetted tidal disruption events, where you also these effects would be important. So now just to summarize that, we had like the difference between the PP and PP gamma interactions depending on the gamma target, or if you have PP or P gamma, and also potential like secondary cooling affecting the neutrino spectra. Now, this flavor composition is also interesting because you can use it actually to test like the physics of the source. And sometimes there are these kind of like ternary diagrams shown here, which were actually invented by Gabriela, who was giving the other lecture, and Chris Crick in 2003. There you see the earthly composition of the neutrinos. So this is the fraction of electron neutrinos at the Earth, muon neutrinos, and tau neutrinos. And they can range, of course, from 0 to 1 each. But since they are not fully independent, the sum has to add up to 1. You have this kind of like ternary diagram, sometimes called Dalitz plots. So in one of these points, you can basically go along these lines to read off the flavor composition. There will be like 70% of electron neutrino at this point, 10% of muon neutrino, and 20% of tau neutrino. And it turns out that flavor mixing, so this is illustrated here, that's like average neutrino oscillations. So what happens here is that you have like an initial flavor. You project the flavor on the mass eigenstate in an incoherent way. Then you propagate the mass eigenstate and you project on the final flavor in an incoherent way. You have to sum over all intermediate mass eigenstates. So that's average neutrino oscillations, or the technical term actually is flavor mixing. So if you write a paper, don't use average or neutrino oscillation, but use flavor mixing. That actually leads to a kind of like an equilibration. So whatever you have at the source, you kind of like any fantastic flavor composition among whatever active neutrinos you want to picture, and you do use the flavor mixing, you would actually end up in this gray-shaped region here. So that means you cannot occupy all of the parameter space. You can, of course, try to measure that. I mean, IceCube has done that, and there are different like versions of that in the literature, actually, where you see, for instance, the 1, 2, 3 sigma counters, and there, of course, they don't care about, like flavor mixing or so. They just constrain the flavor composition. You see also some kind of like structure here. For instance, the tau neutrino fraction is not as well constrained as the others. So that's interesting. You can also like think about cases where you have at the source. So that stands for the flavor composition at the source, different like versions of flavor compositions. For instance, the famous muon damped source would be the purple one here. And the purple one is this region here. So that is like what you would expect in that case, where these different colors here stand for the different like for the mixing angle uncertainties. So this is like the 1, 2, 3 sigma uncertainties of the mixing angles. So you see, I mean, the standard model would occupy a relatively small fraction of this parameter space. And of course, it has been discussed in the literature that if you have like deviations from that, you find yourself like let's say there or here or there, then maybe this is an indication for physics beyond the standard model, which is relatively robust in the sense that it does not depend so much on the normalization of the source flux. So it's like, because this flavor composition doesn't care about that. The disadvantage is it's relatively difficult to measure, as you can picture here. So this is a projection for IceCube Gen 2. So that's interesting and has been extensively discussed in the literature, but it's of course not. Now it's. You can call it oscillation averaged, but don't call it neutrino oscillations, because some people are sensitive to that term, so they would like put that in a different corner, you know. So it's like typically, I had to change the title of a paper once because of that into flavor mixing instead of like neutrino oscillations, because it's not actually oscillations happening there. Okay, of course, I mean, this is not the only way how we can test like physics beyond the standard model. Maurizio here and some collaborators were producing a nice figure, which I never fully understood. But anyways, you see that you can you can test like neutrinos, physics beyond the standard model, affecting the arrival time, the energy spectrum, the arrival directions, or the composition. And there are different types of beyond the standard model physics models, which you find here, classified into like acts during propagation, production, and detection. And then there are a lot of like curves connecting these two different points, which are kind of like, I guess, educated guesses how this could be connected, but I don't know if there's a systematics in that, but Maurizio can probably answer that if you ask him later. Okay. Now, the last slide of this part of the lecture I wanted to touch on was let's say, typical propaganda plot. I mean, I don't know if you have seen this kind of figure where you see the distance you can look at as a function of energy. And it turns out, if you look at the electromagnetic spectrum, like photons, that especially at energies of the order of 10 to the, I don't know, can you read the scale? 10 to the 15 electron volts, which is around here. You cannot see very far. You can hardly see the galactic center. And so the distance you can see is like limited by, especially for gamma rays, for very high energy gamma rays, because they're interacting with the cosmic microwave background and background light also. So this is like what's like this dark region here. And neutrinos, of course, they're not affected by that. They can look like far, far back in the universe. They're not really like attenuated by these kind of effects. So this is like often shown as a like kind of, you know, incentive why we want to look into neutrinos. And I just want to like a little bit give that a little bit of critical flavor here. So on the other hand, you can also think about how much energy you actually need to see one neutrino event. So this is the energy in neutrinos in ERGs, that's 624 GeV. It's a function of redshift. And this is like for different assumptions of the experiment and the neutrino spectra, but you see clearly this trend that for low redshifts, you need very low neutrino energies or energies in neutrinos. For high redshifts, you need higher numbers. We will try to connect it to the gamma rays in a second. You can also see certain benchmarks here for different models, and you see also certain benchmarks in certain distances for certain objects. So this is AGN blazars. That's a tidal disruption event. That's the redshift of NGC 1068, which we discussed yesterday. So the question is, do we really see the neutrinos through the whole universe? And you can already guess here that if we go to like high redshifts, we really need a lot of energy in neutrinos to observe one neutrino event. So we see these neutrinos like in a cumulative fashion, in a diffuse way, but can you really see the source? For that, I mean, there's a couple of concepts which are a little bit more technical, but which I need later, which I want to like look at. This is like related to energetics. So if you wanted to look at the energy which you need to actually power neutrinos, the energy going into neutrinos, it's related apparently to the energy you have in protons at the first place, times a quantity which we have seen yesterday in a certain way already, like the optical thickness to P gamma interactions, for instance, or PP interactions. Optical thickness, again, is giving you like a handle on how frequently you would interact before you leave the source. So typically this number is much smaller than 1 because you would not find as many targets as that you would be stopped there. But if you have like an optically thick source, then this optical thickness would be much larger than 1 here. This could be also not only the size of the source, you could also have like the escape time. So it depends a bit on the model, okay? Then there is like some kind of like threshold factor. Very often, if you look in the papers, in the literature, people forget that neutrinos don't interact below the threshold, like the protons don't interact below the threshold. So there is like whatever, a large fraction of the proton energy dumped into the neutrinos. Kota would call that bolometric correction factor. It's essentially the same factor. You have to be aware that you only have a certain power in this part of the spectrum which can actually interact and go into neutrinos. You can, yeah, I mean, the easiest way is to relate it to the bolometric, like total neutrino energy. Yeah. So you basically have the proton energy, you dump a certain fraction which is related to this optical thickness. There's sometimes a factor 0.2 in front of that, which relates to the fact that you can only you'd only dump 20% of the energy in a pion per interaction. And sometimes people call this 0.2 times tau p gamma like F pi, the pion production efficiency. So that's also something which you find in the literature. Then there is very often a factor 1/8 appearing because you only have like 1/2 of the energy going into charge pions, roughly. I mean, I had this data resonance approximation earlier, which was like 2:1. But if you take multi-pion processes into account, we had this question yesterday as well, it would be rather 1:1. And then the pion decays into 4 leptons essentially at the end, like an electron and 3 neutrinos. So per neutrino flavor, you have a factor 1/8 here. So this is a rough estimate for like how much energy you can have in neutrinos compared to protons. And if you take into account that most sources are optically thin and that you have this factor 1/8 and the threshold connection, I would say typically less than 1% of the proton energy can go into the neutrinos. Okay, so that's just a rough estimate. Of course, if you have optically thick sources, it could be different. Now, the next step is to relate the proton energy to the photon energy. So like, what do you actually observe are gamma rays, for instance, or like electromagnetic spectra. And this is very often done by a fudge factor, which is called the baryonic loading. I call it 1/Fe. You can also call it whatever you want it. But in principle, the proton energy is typically a factor of a few higher than the energy you actually observe in gamma rays. And if you put this in here, up there, then you see that the neutrino energy is typically much smaller than 1% times the energy observed in photons times this baryonic loading factor. And that tells you already that you need a baryonic loading, which is typically much larger than, let's say, 100, if you want to have an energy of neutrinos comparable to gamma rays. So if you have gamma ray observations, you typically have an idea of how much energy the source actually emits. And if you wanted to know how much neutrino energy you get, you have to multiply this with this kind of factor. So you can, I mean, this argument now is a little bit fishy because it's not like very rigid in a way. But you can still do some back of the envelope estimates now. You can see how much energy a source actually emits in gamma rays and try to figure out what that means for this like figure. How much neutrino energy do I actually need? And you can already see at this place, in principle, if you look at the typical energies or luminosities of AGN blazars, that it's, since they are actually optically thin in most cases, that you need like very high baryonic loadings because these things are very distant. So these sources here, they're very far away. The AGN blazars, typically the ones which have been observed at least, they require very high neutrino energies, and you only get that if you have very high baryonic loadings. And in fact, in the models, the baryonic loadings are sometimes fantastically high, like whatever 10⁴, 10⁵, whatever for the TXS blazar. Gamma ray bursts, on the other hand, are expected to have like baryonic loadings of the order of 10 to 100 from the ultra high energy cosmic ray connection, if they are the sources of the ultra high energy cosmic rays. But you also see here on this scale that if you take this kind of like number and you compute the neutrino energy, gamma ray bursts, I mean, these are typical gamma ray burst models, but gamma ray bursts emit energies in let's say in gamma rays of the order of 10 to the 53 ergs, let's say. If you wanted to have like a baryonic loading of 100, that would be also coming out into neutrinos. So you see, you would see until a redshift of, let's say, beyond 0.2 or 3, but gamma ray bursts typically live like at higher redshifts. So that means it's probably not expected that you would actually see neutrinos from individual gamma ray bursts because they're simply too far away and not putting out enough energy per GRB. On the other hand, like nearby sources like NGC 1068 or the galaxy, which is even nearer, don't need to put out a lot of energy in neutrinos to actually see them because they are nearby. So they are the less luminous sources, but nearby sources. So at the end, what you need, if you really wanted to see the neutrinos, is either something which is very nearby and not too luminous, or something which is very powerful or far away, or something which sits at the sweet spot. And at the sweet spot are actually these tidal disruption events I'm probably going to talk about tomorrow. So these are like in the intermediate range here in redshift, and also like in the intermediate range in terms of like energy output. So they sit sort of like in this spot, which is in between these two. So at the end, the qualitative point or semi-quantitative point, apart from these things, which you should probably remember because they will also show up like tomorrow again, is that although neutrinos can travel through the whole universe, it's only realistically possibly to see them in either very nearby or very bright sources, or individual sources at least. And that's also like what we have seen so far. So you cannot expect like sort of like neutrinos from all sorts of possible sources which may potentially emit neutrinos, because there may be actually much more neutrino emitters than we may think about, but you have to satisfy this criteria. So that's a little bit, you know, like this kind of like a comparison between this picture and that picture. So this is true, but, you know, you also have to consider energetics to some degree. Okay, so that was essentially the first part of my talk, lecture. I want to skip this. So actually in the next part, I want to, are there any questions to this point? Maybe that's a good point to, yeah. There are two actually.
Yeah, so I was wondering about this energetics, the energy versus redshift. Is that basically just the distance from the source to us, and then because it's so far away, you distribute the neutrinos over larger area? Is that where this is coming from, or am I missing something?
No, it's just the distance in this case. So here we talk about individual source detections, and that's the distance. But of course, you are right that once you go further away, the volume increases, and then you get more sources. We will see such an effect maybe later or tomorrow in one of the cases, right? You would see that.
Okay, but for an individual source, this increase in energy is
it's the power requirement which comes from distance, right?
Okay.
Yeah.
All right. Thank you.
Actually, I have two questions. One relates to this one because we're not taking into account the solid angle, right? Because neutrinos need to be beamed to us. So you need to meet this criterion, the energetics, but you also need to see the neutrinos that come from the point source, right?
I mean, what do you mean by solid angle? The solid angle of the experiment, or like the beaming of the source?
The beaming of the source.
I mean, this you can factor in there. I mean, you can interpret this as like isotropic equivalent energy in neutrinos. Okay.
Okay.
So that's relatively easy.
Okay. And the other question was for the muon dump scenario. And I saw that there is this very small window in energy that, yes, here. To have neutrinos only from muons and then neutrinos only from pions. And I was wondering, how can you nail down this small window in energy to actually discriminate or discern this scenario, the muon dump scenario?
I mean, in practice, of course, you have different sources contributing, and there will be like some kind of smearing out. But there are also, even in IceCube, of course, considerations to nail down this effect by putting like a cut in energy and then looking at the flavor composition like at low energies versus at high energies, as far as I understand. So they, I mean, they're trying to look for this kind of effect. If you make a cut here, for instance, at a reasonable energy, whatever that would be. So this is like in E prime. I was hiding this fact a bit. E prime is the energy in the shock rest frame. So you have to boost this by the Lorentz factor of the source as well. So maybe a reasonable number here would be like 10 to the 5 or 10 to the 6 GeV as a cutting point. Then he could try to search for this effect. And of course, it would be like a unique indicator for like a source class with strong magnetic fields, like for instance, a tidal disruption event or a GRBs, like low luminosity GRBs or something like this.
Thank you.
There was one more. It's answered already.
Okay, all clear? More questions? Yeah.
I was just wondering on the energetic slide, if you could explain a bit more about the 1/Fe baryonic loading factor. I just didn't quite understand.
I just can't hear it. So.
Oh, I just wanted to ask about, the energetic slide. I wasn't sure exactly what the 1/Fe factor is supposed to be, like the baryonic loading.
What it is?
Yeah.
Yeah, I mean, in principle, it's just like. So we don't know, I mean, this is like just like a relationship factor. So what we know about the sources is typically the output in gamma rays, because we observe electromagnetic radiation, like gamma rays, for instance, or like in the optical range or whatever, right? So this is what you see. We don't see the protons directly. So we don't know what actually the energy in protons would be in the source. And in order to parameterize that, we use a factor which is called the baryonic loading. You can think about, about possible other ways to constrain it. We will come back to that later for the AGNs, for instance, or also for GRBs, perhaps. Like there are different ways, like, for instance, from the ultra energy cosmic ray connection, or from the relation to the Eddington luminosity or something like this. But at the end, for us here, it's like a fudge factor, which is something which we have to fix as an input parameter of the model at the moment, because we can't measure it directly.
It's essentially just like the density of baryons in the environment.
In a way, yes. I mean, or the injection luminosity of protons, non-thermal particles, non-thermal protons. That's very important. Like, yeah, I mean, we come back to that a little bit later in different contexts. I will try to come back to that whenever it pops up. Okay. So maybe we continue first, and then we discuss later this afternoon. Yeah. Okay, because some of your questions will be answered later. So now in the next lecture, sort of our part, I want to discuss multi-messenger follow-ups. So that's a little bit more astrophysics related, because now we actually talk about particular source classes. And one source class, which is interesting for you, also because you will have a couple of talks on that in the afternoon, are AGN blazars. But it's not only that one. So one prominent example of that class, which was found in neutrinos, was the TXS blazar. So that's this one here. But also tidal disruption events could be interesting. So in this case, the idea is that the neutrino signal would trigger other instruments. You would look into that direction, you would see something, then you can relate the neutrino directly to, let's say, like an optical or a gamma ray counterpart. So that's what this gamma ray follow-ups are about. And as I said, the next part is essentially about AGN blazars, where there are also a couple of talks in the afternoon. An AGN blazar is like looking into an active galactic nucleus, ejecting a jet, and you would look into the jetted direction here. So you look, the observer is sitting somewhere here. I will like qualify that a little bit better in the next slide, where you have like a cartoon picture actually of an AGN blazar. So in the middle of the AGN blazar, we have the engine, and the engine is a supermassive black hole. That means a black hole which has like whatever 10 to the 6 or more solar masses mass, like very, very powerful, which sits right in the middle. You can easily, you cannot see it, of course, because it's a black hole. You can see black holes, that's clear. There is potentially like an accretion disk around it. So that's material which is like basically sucked into the black hole here around this black hole. And there's like larger structures around it, like a dusty torus, perhaps. There are some clouds, which are also like measured indirectly by the emission lines, like so-called broad line region or also narrow line regions. And you have this jet, which is by some kind of mechanism. I mean, there are some mechanisms in the literature which can describe that, of course. You can translate essentially this kind of like rotational inertia or like this energy in the black hole into a jet. And we look into the jetted direction here, if we call it an AGN blazar. If you talk about an AGN core, which will also show up later, it's essentially the inside region here, okay? So like closer to the supermassive black hole. There are theoretically like two interesting quantities in that context. One is the angular momentum, because that determines the geometry and also the jetted direction. So if the jet goes in that direction, probably the accretion disk will carry some angular momentum, which is like going in this direction also, or the black hole. I mean, there's some relation between these. The black hole may also have a spin, actually, as we know. The other one is the so-called Eddington luminosity. The Eddington luminosity is like a measure, like coming from a different context. It's actually estimated for like a spherical object, but it is a measure of like a balance between power of accretion or like inside gravitational infall and gas pressure. So it's like a power of like how much energy you can accrete over time. And it's a power also, and this is how we interpreted it, which you can interpret as like a measure for how much energy you can actually process through the supermassive through the accretion disk supermassive black hole system. So that means this Eddington luminosity, which is related to the mass of the supermassive black hole. So for a 10 to the 9 solar masses black hole, you have like a 10 to the 47 ergs per second, is a measure for how much energy I can take out from the accretion system and put into like components like the jet or something like this, or non-thermal particles. So if I exceed this number by far, I will probably have a problem with my accretion models. If I kind of satisfied or only have like a small fraction of that, it's easy. So I mean, astrophysically, that's perfectly sound. So that's like why this quantity is kind of interesting, but don't forget, it's just like a rough estimate for what's going on. And there are systems which are so-called super Eddington systems, of course, where you would exceed this. Like in tidal disruption events, you could exceed this by a factor of like 100 to 1,000 over a short period of time. But this is always an indicator for something massive going on, like an explosion or something like this, you know, if this is exceeded. In equilibrium, you would expect that this is kind of like the luminosity cannot exceed that. And that comes back to your question in a way. So this would also provide you a measure for how much energy you can actually have, like in protons, as one example in these systems. Okay, so how do AGN blazar models actually look like? That's now the astrophysics perspective. So we measure these kind of spectra as a function of either frequency here on that axis or energy, as we prefer typically in astroparticle physics. This is again E squared times the N over dE, a spectrum as I showed it before. Sometimes the gamma ray people or the electromagnetic people call that nu F nu, like, but it's in principle the same units. And you see that you measure like the spectrum in different wavelength bands, which are here in different colors, by different instruments as well. So which I also illustrated here. So that would be like an X-ray satellite. That's like a typical radio array, which is like measuring in that energy range. Optical are like telescopes, the ones which you actually can, I mean, optical is like, of course, something you can see, but you need like large telescopes to look into like far, far away. You have like gamma ray satellites, which are measuring in that range. And then at the highest energy, so-called Cherenkov telescope arrays or imaging atmospheric Cherenkov detectors, like the Cherenkov telescope array would be like your choice. So that they measure essentially the interactions in the atmosphere and the shower, which produces light in these cases of these high energy particles. So you see, you measure typically the source in different wavelength bands, and you try to put like a theoretical model behind that. And the baseline theoretical model is the so-called SSC model. So this is a model where you put like high energy electrons in the system, so-called non-thermal electrons. That will be the electrons which are accelerated by Fermi acceleration, let's say, through some kind of like spectrum e to the power of minus something. And these electrons, since electrons are very light and they have a relatively high charge for that, they shine in synchrotron radiation. So it's relatively easy to get a synchrotron peak here, which is determined by the synchrotron radiation of the electrons. And then you could have like actually the same photons which you produce here could serve as a target for the same electrons you would inject here. And you would kick up the energy of these photons to higher energies. So this electron would actually lose energy and the photon would gain energy, which produces a second peak here, which is a so-called inverse Compton scattering peak. And this model is called synchrotron self-Compton model because you're scattering off the radiation itself, if you wanted. So you scatter up the photons which you produce here by the same electrons to higher energies to get this double hump structure. And in fact, it describes most of the AGN blazars almost perfectly, let's say. Sometimes you don't fit the radio data because they're believed to be coming from a different, like larger region, so they don't fit this picture. But apart from that, I mean, this double hump thing is something which you would describe by these effects. So this, of course, is nice, but as you can see, there are no neutrinos involved in the game and no protons. So it's not so interesting for us, actually, as a first approximation. So just to remind you from yesterday, there are other processes where actually you have protons involved, like we have the photopion production we talked about yesterday, but protons may also do synchrotron radiation for in high magnetic fields, at least. There are other processes like Bethe-Heitler pair production and so on. But at the end, if we wanted to have neutrinos, we need probably photopion production in these cases, which would also come with pi-0 production, of course, which would inject like high energy gamma rays. And also electrons are like coming in this cascades here, which will be part of the story. So if we wanted to have protons, we have to face with these processes as well. Then you can come up with, let's say, more exotic models, which also involve like the protons. So as I said before we had these SSC models, for instance, where you have like leptonic peak and another leptonic peak. You could also think about, if you can't describe your model, perhaps I need some other radiation, not this radiation here, but something which I put in from the outside. And then I have more parameters and I can describe my radiation. So that's called external Compton models. That's also a leptonic model. But at the end, the idea is that all of this is leptonically created. A very popular model for a long time is the so-called proton blazar model. So that was a model which was postulating that perhaps the pi-0 decays at the higher energies, which are coming together with the neutrino production, could produce the second hump here. So that would be like of hadronic origin in this case, where you have protons in the system. The protons would produce also neutrinos, but not only that, but also pi-0s. And then you would have like an hadronic peak here. Another popular class of models is that you have proton synchrotron radiation actually describing the second hump. So that would be not as directly as that, probably related to the neutrino production, but probably you would also produce neutrinos here because you have protons and you also have target photons. So that's also clear. And nowadays, I think it's also fair to say that there are more exotic models where you have like different types of processes actually contributing. That's just like one example here. We will see one of these later. At the end, what you do is you describe your physics in this radiation zone I was talking about yesterday. In this case, these are so-called like spherical cow models, if you wanted. So you have a spherical region, radiation zone, like a blob, which you then throw with a Lorentz factor later towards the observer. And all of these models, or most of these models, have in common that they are like more or less simple in this geometry. There are sometimes like extra ingredients or so, but it's relatively simple. So a lot of stuff goes up into solving these equations I showed you yesterday, plus putting these processes, also implementing them in a kind of like efficient way. And then you would try to solve this and for the electromagnetic radiation and for the neutrinos. So one thing you see here already is that since I focus a lot on the electromagnetic radiation, that's like the multi-messenger context, the point is whatever you do with your neutrinos, I mean, if you observe neutrinos or not, or you predict, or you want to explain something, you cannot, or you must not screw up the electromagnetic picture. So you cannot just assume something out of the blue without being able to describe the electromagnetic radiation, because that is something which has been measured very solidly. And on the other hand, the neutrinos, maybe you have like an event or no event, or maybe whatever, 0.1 event or 0.01, or I don't know. You may have seen something or not. It's more like, let's say, fuzzy. So now let's go a little bit to observations. So the TXS 0506 plus 056 is the most prominent example of that class. There on September 22nd, 2017, a neutrino was found, which was entering the detector like this here, where again, blue is early in this case, and this yellow here is like late. And you trigger the detector. You have a very beautiful muon track in this case, which would give you some directional information, which is illustrated here as a function of right ascension and declination. You see the error region of the ice cube event at different confidence levels. And in fact, there was an AGN blazar found in the middle, the TXS blazar with this catalog number here, right in the middle. So it's like a very beautiful event. It has been observed also like in correlation with that neutrino event by Fermi LUT, like in very high, not in very high energy gamma rays, but in gamma rays, and in very high energy gamma rays by the MAGIC telescope. So that's like one of these imaging atmospheric Cherenkov telescopes measuring like in the TeV range. The significance for the correlation is relatively high, and the redshift is also not low, but not super high. I mean, remember this kind of like energetic plots I showed before. You probably don't want to be at too high redshifts. So 0.33 is probably not so bad. So this shows you a so-called spectral energy distribution. So SED in technical terms stands for spectral energy distribution. So that's again as a function of frequency or energy, the data. And the data in these astrophysical kind of plots are sometimes difficult to read. So what you see here is in fact as gray dots in the background. So they're deliberately gray because they're so-called archival data. The problem is that you don't measure these sources like at the same time when you need it. So the neutrino came, you measure like your gamma rays. In fact, it turns out that you have a so-called flare here, a gamma ray flare. So that it is an enhanced activity in gamma rays compared to the archival data. But only these data are like coming together with the neutrino in the same time slot if you want it. Also the other colorful data, whereas the rest of the data, the gray data, are taking, let's say, arbitrary times. So you have them in the archive somewhere. So you can compare to that, but you want to understand if the source was in some kind of like special state when the neutrino arrived. And this is what's illustrated here by this enhancement here. So apparently there's a gamma ray enhancement at the time of the neutrino arrival, at least compared to like some kind of archival data at some time, which you don't know a priori if you look at the figure when that was actually taken, or if it's like some average or whatever. You also see in this case the MAGIC data here and some other limits by other experiments. So colorful data points here are like inconsistency with the timing of the neutrino event, and the gray ones are like like archival data. And the neutrino event, like sort of level, is illustrated here by these different error bars. So it's like here a little bit of a question, like how long time you're taking, if you're only taking like at the time of the flare, or if you take the full operation time of the experiment. At that time, there was not really known. So what we know is that the gamma ray blazar, the blazar was like in an enhanced gamma ray state of the time at the time of the neutrino emission, and that made people believe, oh yeah, there was one neutrino. We looked in that direction, we saw the blazar, it had an enhanced gamma ray state. That must have been like a neutrino emitter. Okay. And it's interesting because actually it goes a little bit further. Then what they did is they did an analysis in the same direction and looked further back in time. And they actually did like an analysis like in time here, as you see the time series with different assumptions for the time-like shape of this signal, where they found in 2014-15 even more significant excess of neutrinos, like 13 events with a significance of 3.5 sigma. So this is like the 2014-15 flare of these neutrinos compared to the one which was in 2017, which was only one event which was seen there. And that was interesting because now you looked like in a certain, you had a neutrino trigger, you looked in the direction, you had a gamma ray blazar, the gamma ray blazar had a flare, you looked back in the time, you found like an enhanced neutrino signal back in time. Unfortunately, there was no gamma ray flare at that time. So that's the gamma rays flux as a function of time. You see the 2017 flare here in gamma rays, and there was in 2014-15 no gamma ray flare. And that's probably still a puzzle, if you can call this like a, like evidence then, or like if it's really related or what it is and so on. And it's disputed also in the community if, like if you can call that, really like coming from this AGN blazar. So this is something you can think about yourself, but at the end, it's an interesting event. And probably some of these neutrinos are also coming from this blazar. So there's one additional aspect to that, which is kind of experimental as well. I just want to open this calc briefly. It's a little bit complicated, but I think it's a substantial difference if you observe like one neutrino event, like in 2017, compared to like observing 30 neutrino events, because 30 neutrino events means you cannot mess a lot with your models. I mean, you have to predict some neutrinos. One neutrino event could mean that maybe there's each source only emits like, let's say 0.01 event, and you have 100 of these sources, and by accident, like you see one of these, okay? And this is like they tried to quantify that with the so-called Eddington bias. So if you distribute your many sources in the universe and you see like one event, which you see here in blue, and you want to know how many events does each source actually like emit, then one event basically translates into far, far away. So that means many sources must contribute because the universe, the volume increases if you go far, far away. And each source probably emits only like 10 to the minus 2 or maybe even fewer events. And then they contribute all together like this one event. And it was like pure accident that you have seen that. Whereas if you have actually, let's say, 3 events which you observe from the source, then the number of expected or detected events is also of the order of 3, or let's say 1, 2, 3. So that's like in a way like also a manifestation of Poissonian statistics. So that's interesting because that makes these two cases also very qualitatively different, because here you can play, you know, like with models which predict like 0.01 event or whatever, but you cannot like do the same here. So that indicates already that probably something is, you know, not consistent there, or perhaps I didn't want to say that, but maybe qualitatively different at least, okay? So let's try to interpret that a little bit, you know, like what happened there, like from a theoretical perspective. I showed you already this kind of like figure from before. They have like the typical like electromagnetic model, the synchrotron self-constant model for, in fact, this TXS blazar. So that's for the flaring state. So what I showed you before was already for this blazar. Where you have an electron peak and an inverse Compton peak, which is nice. It beautifully fits actually the data during the flare, but of course you don't have neutrinos, so it's not so interesting for us here. The proton blazar model, if you wanted, if you feed actually this high energy thing with the pion cascade, like the pi0 decays, that's neat because you can in principle describe data. The problem is, however, that you would also produce, for instance, Bethe-Heitler pairs. You have electron-positron pair production, or you produce also in the pion cascade electrons and positrons. And these electrons, they shine again in synchrotron radiation, and you get a whole mess. And it turns out that you cannot like have a clean peak here without creating a mess at lower energies. And in particular, this data here, they have this dip in the X-ray data, where essentially the energy flux is low. And whatever kind of like mess you create at higher energies will, through electromagnetic cascades, feed into this energy range and will screw up your X-ray data and potentially also TeV gamma rays. So that is something which was realized relatively early after this TXS blazar. And I think that's also like one of the biggest paradigm shifts from this kind of observation, because that's now in principle true as zeroth order paradigm for everything, for all HEN blazars. The neutrino signal is here. You see it's relatively high compared to the IceCube observation. But one thing you see, and you will always see that in the future as well, is that once you have neutrinos at this level, the gamma rays which are coming like with the same kind of processes are also at a kind of similar level. So the neutrino flux and the gamma ray flux, they are related, as you remember, like for instance from the earlier examples, and that means this is like a good indicator like how high the gamma ray cascade should be. And then, so that means at the end, what you have to do is you have to take your constraints in the X-rays and the gamma rays seriously. And at the end, these will constrain the hadronic contributions. Hadronic contributions are blue in these figures, the leptonic ones orange. So they are limited here. And that will also limit your neutrino flux to a similar level. So here you again see the level of the hadronic contributions, and then the neutrinos are kind of similar. So the conclusion was that for like the baseline models, you know, for this TXS blazar, you would actually violate energetics a lot, like the Eddington luminosity, which I mentioned in the beginning, or you would need also like translate it into you would need to translate that into a very high baryonic loading. So for these standard models I checked, the baryonic loading was larger than 10 to the 4. There are even models which have baryonic loadings higher than 10 to the 6. So very high, because you need this very high energy output in neutrinos, which I showed you earlier. So I don't want to go into further details because I have time, but people were playing with that in all different ways. Like you could have like external radiation fields or compact cores or like additional clouds to actually circumvent this like energetic constraints, but that only makes the models at the end more complicated. Now, just let's have a look at the historical flare, which I think is even more interesting. So for the historical 2014, not flare, neutrino flare, it was not a gamma ray flare. So for the historical 2014-15 neutrino events, you would have like actually a high measured flux, which is illustrated here as a neutrino flux. And remember that we had this like relation between neutrinos and gamma rays. So if you inject this many neutrinos, you would also inject like electromagnetic radiation at the same level. So it would be expected to show up somewhere at this level here. But what has been actually measured at that time are the colored data here. So they are substantially lower by 1 order of magnitude. That's similar to the NGC case, which you remember from yesterday, where we had a similar problem. So that means that probably you have to have some kind of like absorption going on in the source, but absorption alone is not an explanation. Absorption is often used or pulled by many people as explanation, but it also means the radiation is not going away. It has to be going somewhere, you know. So does it show up perhaps in this energy range where we don't have data at that time, or what does it do? What's happening there? And I'm just listing a couple of possibilities here. For instance, we may have like this kind of like energy reprocessing. We could dump energy like into extragalactic background light at high energies. So if the source is optically thin, they would interact with the CMB and it would be absorbed there, or other like possibilities. But you have to invent something to actually explain that. And I want to just show you like one example, like how this can be done. So this is one of the more exotic models where you would actually have the data if you wanted. I mean, the theorists are not stupid. So you can play with the models in a way that you would scan the parameter space systematically, and the fit would tell you what is actually the best fit, for instance. And the best fit in such a case, if you have like sparse data, is, for instance, you would park the energy in an energy range where you don't have data. Okay, so here again, you know, like you have the ice cube level of like electromagnetic cascade emission coming here. It would be reprocessed in the source and it would show up here. So that means that at the end, if you really wanted to monitor these kind of like neutrino emitting models, you actually need like data in the whole electromagnetic energy band, because you can always come up with some kind of models which would like park the energy wherever you need it. And you see also like the different processes contributing here. It's actually non-trivial. So they're like, for instance, this hump here is coming from a gamma-gamma to electron-positron pair. And then you have like synchrotron and inverse Compton scattering of these processes. Like that's the synchrotron peak and the inverse Compton peak. So it's kind of complicated, and you can come up with all sorts of different like versions. Don't want to go into further details there. Maybe this is also a relatively good point to stop here, just to like maybe finish with that. So here you saw that I only produced like 2 neutrino events. You can also have a little bit more neutrino events if you invoke additional radiation fields. Like these AGN blazars are in fact like typically embedded in environments where you would have this broadline region, which I was showing before. So if you have, for instance, radiation, which is scattered back from the accretion disk in the broadline region, and the jet is running into that, then these external fields, which you would see as an observer, like as suppressed fields in your direction up here, actually from the point of view of the jet get enhanced because it's scattered back and you bump into that. I mean, it's a head-on collision. And this could also enhance your neutrino production efficiency. And then you can actually get a substantial number of neutrino events in that range. So that means there are models which can sort of like describe these data, but you have to like pull a couple of tools from your, let's say, toolbox in order to make this work. So with that, I may finish now, perhaps. I wanted to discuss as next steps a bit like diffuse neutrino fluxes from AGN and tidal disruption events, perhaps. And then I think I will do that on Thursday, and then perhaps discuss a little bit of like a cosmogenic neutrino production. So that will be sort of like the end of the lecture series. Thanks.
Thanks, Walter. Do we have questions? And I also have an eye here on Zoom. Don't see any questions there at the moment.
I mean, I will be also here for the rest of the week. If you have questions, we can discuss also this afternoon.
And this evening, we also have again this last session where
Exactly.
we get together.
Yeah.
Okay. That's it.
Yeah, for those archival neutrino events coming from the TXS source, what is the directional uncertainty on those? I mean, does it necessarily have to be correlated with a flare of TXS, or is there something else that could be in the uncertainty region that has a flare?
I mean, as far as I recall, there are people who have like discussed other alternative sources, which would be like, you know, like close by also like contributing something, but I don't know how the directional resolution compares to the 2017 event. Maybe Marcus knows because he's an ice cube.
So the was 200 and good resolution, and we also saw that this is very clean in those two. For this 2014 15 there, this was more on the lower energy side, so 20 eV, and angular resolution there is not as good as that. That would be more than half. And as I said, there are a lot of sources, of course, in any spot on the slides, there could be some potential as well. Okay.
So this has been discussed in the literature also, so there have been people looking into that. So.
Okay. There's one on Zoom.
Is there a question?
Maybe a question.
Oh, sorry, I'm standing in front of the camera.
Yeah, okay. So there is a question by Jesus Cesares. So Walter, you commented about to observe all of the electromagnetic spectrum. I observed that you put an experiment at radio frequencies VLA. Do you think that exists the probability to observe neutrinos at low frequencies?
Yeah, so for the radio data, I mean, this is something I mentioned only very briefly, but you can see that also in the in some of the figures. Here they are not, but typically the radio data are not very well described by these models. So here you see some radio data, for instance. So this is like a frequent problem in AGN radiation modeling, that the radio data by this SLC models even would not be well described, and you would need to invoke additional like contributions like a larger region or so, which would describe the radio data. So I don't know if the radio data are really a good indicator for the neutrino emission, because first of all, it's not easy to actually repark this energy to such low energy if you want it. There is like effects going on like a synchrotron self-absorption or other things. So, and also the radio emission, which is actually observed, may not come from the same zone as the neutrinos, because the neutrinos require like a compact radiation zone with a high target photon density. Which would also create all these kind of like energy reprocessing effects in the electromagnetic cascade, whereas the radio data are in fact kind of probably coming from like a larger region in both cases. So I don't think that the radio data would be the prime indicator. It's really like more like a KeV to MEV gamma rays, X-rays to KeV to MEV gamma rays, and then maybe, or like X-rays, depending on how you call them. And then maybe like very high energy emission in the Cherenkov telescopes, if it's nearby enough, which it's typically not.
Okay, Jesus says thanks. So that answered the question. Any more questions here? Yeah, maybe one last question. And then
Okay, maybe this is an absurd question or something like that, but do we know if there's objects that could potentially create different kind of, I don't know, either neutrinos or photons that we don't know yet, or we haven't observed yet?
Yeah. I mean, there's a plethora of different objects. I mean, I focus on in my lectures, like in whatever, I mean, because it's a personal matter of taste. I tend to like focus also in my research more on objects which I find less speculative, because they have been well measured. You know, there is like evidence here for neutrino emission. We have like electromagnetic data in wide wavelength bands. But of course, once you go like to objects which are less known, like let's say, you know, like F-bots or like, I mean, there's many new sources discovered in astrophysics. We have also like low luminosity GRBs, different classes of GRBs. We have like possibly different populations of that. Then it's getting more speculative. You have more freedom, of course. And this you also see in the modeling. If you look at the theoretical models and you look at arXiv, there are frequently models for neutrino emission on this, that. But the more freedom you have, the less constrained you are. And it's also maybe, I mean, it's a matter of taste, if that's like as interesting as the established stuff or less. But for these kind of sources, I mean, they're also interesting because they have been established as potential candidates, let's say, for instance, for ultra energy cosmic rays, like gamma ray bursts are one of the main contenders for that. And then the question is, of course, why don't they emit neutrinos also? Yeah. So it's a matter of motivation. And if you ask somebody else, for instance, to give this lecture series, you may also get a different answer. Like they may walk you like through 30 other options which could emit neutrinos. But yeah, you know, it depends on like where you have data and what you actually can learn from that. Yeah, in my view.
Thank you.
Okay, let's have a coffee break. Thank you, Walter. Let's have a last round of applause. And we